Approximate girders are taking girders out of a system. So we've got two columns here with a girder in the middle, and in general, most buildings are designed loaded with evenly distributed loads. Now we've got this girder fixed to these two columns, so it is indeterminate by the third degree, because I have 3 reactions on the fixed ends, right, and 2 fixed ends. But the columns can move. So when I load this, we're going to have some sort of deformed shape created where these are bending down and bringing these in. What this actual girder and column shape does is it deforms a little bit like fixed ends, which is what we have here, where it goes out straight, comes down, and then comes back up here. And this distance is about 20% of the length. And that's symmetric on both ends. And a pin-pin connection where we have the elastic curve looks something like this, where it starts rotating at 0 times the length, right? So we have something between those two, which is what's happening with this girder and column. So our approximate method is going to be something like the elastic curve bends down like this and comes back up. And this distance is somewhere between fixed and penned, which would be about 10% of the length. And when we know those points of inflection where the moment is going to be 0, then we can solve now a determinate system where we have approximate pins now that we can consider here with only shear and normal reactions instead of shear, normal, and moment. With that 10% distance for where we're putting a approximate hinge so we can ignore the moment, we're also saying that the axial forces can be ignored. Of all the beam things that we have done in this class, we see that the axial forces have very little effect on beams and girders. So we're just saying that it's so small now that we can neglect it. So all we have to worry about are moments and shears. And the moment at 10% of the length we're going to approximate is 0. So how do we put this into practice? Well, let's say we've got this girder and column portal here, and we want to draw the moment diagrams for girders A, B, B, C. Now we can't do that because A is fixed, B is fixed, and C is fixed, as is D, E, and F. So we can approximate that at 10% of the length, we're going to have 0 moment. So 10% of 4 meters is 0.4 meters, 0.4 meters. And then over here, 0.6 meters and 0.6 meters. From experience, we know our moment diagram is going to look something like this, where it's going to cross at 0, that we are assuming is 10%, that's our approximation, and then it comes up here, and then it goes back down. So what do we need? We need the peak points in the middle, and we need the moments at the reactions at A, B, and C. And we are going to do that with our approximate method. Starting with girder AB, I'm going to split it up into 3 parts. So I have the left section here, which is 10% of the length, 0.4 meters. I have the right side, 0.4 meters. So my middle remaining is 3.2 meters, okay? I've also assumed that at 10% of the length, I do not have any moment. So internally, I am going to have shear. I know, y'all are getting on to me for the directions on the right side. It's not positive sign convention, but I have to start with the middle piece. and the middle piece, symmetrically loaded, symmetrically supported, I need to have shear up on both sides for this to work out. Okay, which means the equal and opposite on the other sides. And I have fixed ends at A and B. So I'm going to have shear at A and moment at A, as well as shear at B or BY and moment at B. Again, I'm going against positive sign convention because I know that compression is going to end up at the bottom so that my moment diagram can look like the purple lines up here. Starting with the middle piece, symmetrically loaded, symmetrically supported, so my shears are going to be symmetric. So that means it's going to be 3.2 times 8, that's the whole load, divided by 2. So I'm going to have 12.8 kilonewtons on either side of my centerpiece, okay? Meaning equal and opposite, I'm going to have 12.8 kilonewtons at that 10% length V. Now with that, I could look at either piece A or piece B because this is symmetric, so I'm going to have the same answers. And if I sum for forces in the y direction, I'm going to have shear at A minus 8 times 0.4 minus 12.8. So my shear at A, which by symmetry is equal to shear at B, and that's going to equal to 16 kilonewtons. But I want the moment, so let's go ahead and solve for that. Summing moments about A, I have the moment at A minus 8 times 0.4 times 0.4 divided by 2 minus 12.8 times 0.4. And I have my moment at A, which in magnitude is going to equal to moment at B. And those magnitudes equal to 5.76 kilonewton meters with compression in the bottom. This is the beauty of the approximate method. There's not a bunch of statics work here because most of it is just visual. The next thing I need to complete my moment diagram is the middle piece. So I'm going to take my section here, the 3.2 meter, and I'm going to section it once again in the middle. Half of 3.2 is 1.6 meters. And this is a middle section, so we are going to have shear, axial, which is 0 because that's what we're assuming, and moment, which we're pretty sure is going to be compression in the top because that is our assumed moment diagram for this approximate method. And I'm just going to call this E. So when I sum my moments about E, I will have minus 12.8 times 1.6 plus 8 times 1.6 times 1.6 divided by 2 plus my internal moment. And I solve for my internal moment. Do I need to give it a name? AB max. And this is equal to 10.24 kilonewton meters. I did get a positive answer, which means my assumed direction is correct. This takes care of section AB, so I'm going to do the exact same thing for girder BC. Each of the sides is 10% of the length, so that is 0.6, leaving me 4.8 meters in the middle. I'm going to have shear acting up here, which means I need equal and opposite on the other side. And then I have my reactions. Shear B, and I'm going to put a left on there because this is a different reaction than the one we solved on AB. Same thing here, moment B left. And then I'm going to have shear C and moment C. Once again, My middle piece, I'm starting with that because I don't have but two unknowns. Symmetrically loaded, symmetrically supported. So 8 times 4.8 divided by 2, I get 19.2 kilonewtons acting on either side, which means I have 19.2 kilonewtons acting on the 10% segment. Summing for forces in the y direction, I have shear B left minus 8 times 0.6 minus 19.2, 24 kilonewtons, and summing moments about B, I will have the moment occurring at B left minus 8 times 0.6 times 0.6 divided by 2 minus 19.2 times 0.6 meters, and my moment B left, which is equal to moment C in magnitude, is 12.96. The last thing that I need is the middle section to get that maximum moment acting between B and C. And getting to the middle, but using that middle section so I don't have to deal with extra moments, I have a distance of 2.4, which is half of 4.8. And summing moments about what I'm calling point F, I have minus 19.2 times 2.4 plus 8 times 2.4, 2.4 divided by 2, plus moment max BC, and I find that value to be 23.04 kilonewton meters. And again, it ends up positive, which means it is compressing the top fibers of the member. Making our moment diagram bigger and prettier to read, I plug in the values that I know: 5.76, 12.8, 5.76, 13.0 in 3 significant digits, and 23.0. These are all second degree curves because a distributed load has a second degree curve moment diagram, and we cross at 10% here, 0.4 meters. And this is the halfway mark at 2 meters. Same thing here, we cross at 10%, 0.6 meters. And this is at the halfway mark of 3 meters. Here we're given a stacked system. So on girder GH, I have 80 pounds per foot, and on girders DE and EF, I have 60 pounds per foot. I have a span of 10 feet for my first section here and a 12-foot span in my right section. Find the moment reaction at B. So just for fun, I put pins at A and C. Does that change my assumed approximate method? Nope, it does not. As long as we have continuous, evenly distributed loads over our entire girder, we can still have the same assumptions for that girder because these are columns that are supported, not the girders. But I want the moment at B. All right. So at B, I'm thinking the best way to do this is to take all my sections here at 10%, okay? If I take those sections at the 10% length, this length right here is 1 foot, and this length is 1.2 feet, right? 10% of 10 and 10% of 12, respectively. I also eliminate having to solve for reactions, and I can just go straight to my shears here. I'm just going to call that shear H, shear E, left, and shear E, right. Okay, so once I get my shears, I can sum for moments about B and get my moment B reaction. Starting with the middle piece of girder GH, I have 8 feet remaining when I take 1 foot from either side. So this will be my shear H, as I'm calling it, and shear H. Shear H, 80 times 8 divided by 2 is equal to 320. And I need to act up on that centerpiece. So over here on my, what is that, a backwards lowercase f piece, this is equal to 320. Moving on to my next girder. I have a smaller distributed load of 60 pounds per feet, but from D to E, my 80% remaining in the middle is still 8 feet. 8 times 60 divided by 2, my shear E left ends up being 240 pounds. My last girder is that middle piece EF, and 80% of 12 feet is 9.6 feet. I'm saying 80%, right? Because if we're taking 10% from either side, that means we're left with 80% in the middle. It is still 60 pounds per linear foot, and I have a shear value of E to the right equal to 288 pounds. Remember, if it's up in the middle piece, then it needs to be down on the outer edges. Now again, I solved it this way because it's a little less math that I have to do instead of solving for the internal reactions up against the column. Okay, I can use that 10% length. Now I can just sum my moments about B. And I find that my moment reaction at B is 241.2 pound-feet. And I got a positive answer, which means my assumed direction of clockwise was correct. I figured it would be clockwise with more of the load being on the left side.